Hello everyone, welcome to the know-how webinars, Q&A with expert. This is a feature of know-how webinars program where our expert will answer the questions received from the participant. As you know, this know-how webinar project is managed by Technobiz, and today our focused subject is on the UFMF membrane filtration. And our expert today is Dr. Graham K. Pierce. I think most of you know who he is, as you have joined his programs or learned from his program webinars, know-how webinars. He's a specialist with a huge experience on the UFMF membrane filtration. Graham, welcome to the program.
Thank you.
Now I'll show you the questions and address them. The questions, these are the questions we receive from the participants, so you address them appropriately so that they get a clear picture of the answer. I will show the question one by one to you and you address them. Okay.
Okay.
There we go.
So the first question is for an out-to-in UF membrane supply with direct flow, so maybe for brackish water RO pretreatment, it provides a very low backwash flow. And an example is given maybe 30 to 35 LMH. Do you think this is a risk? The filtration time is short, say 35 minutes. The flux is modest at about 70 LMH. And the featability is less than 10 NTU around 90% of the time. So the question is this low backwash flow that's typical for outside-in membranes, is it risky? So with pressure-driven inside feed, we were used to quite high velocities in the backwash flow, maybe at least 200 LMH, probably 250 LMH, whereas it's very typical, as the questioner poses, that for the outside-in configuration, the flow rates are much lower. So 30 to 35 is at the very bottom end of the range. There are other outside-in suppliers that would use 60 to 70 LMH, so twice that. And there are others still that use 100 to 110, so 3 times that. So you can see that there's a big range that outside-in suppliers select. 30 to 35 is at the bottom end of that range. These fluxes are a factor of 6 or 7 times lower than what we use on an inside feed. When we looked at the format comparison, we saw that the reason we use such high fluxes in the inside feed is because the velocity is critical. That's what's doing the cleaning. With the outside feed, the velocity is not necessary for the cleaning action because you're reliant on the air scour, and the air scour vibrates the membranes and moves the membranes and shakes off the particles. So the idea of the backwash is just simply to take away those particles that have been displaced by the scour. And so the question is then, is this low flux of 30 to 35 LMH sufficient simply to take away those displaced particles? So I had just given a little bit of thought to this in advance of this Q&A and did some quick calculations. So the free volume of a typical module would be about 60 litres. If you ran at a backwash flow of 30 to 35 LMH, you would be running at 30 litres per minute. That means it would take 2 minutes to completely displace the free volume of the module. Now you can imagine that it would be highly desirable to displace the free volume of the module at least once in the backwash process, because the air scour would displace the particles would fill up the free space in the free volume, and you would want at the very least to completely displace that free volume once at least in the backwash process. So unless you maintained the backwash flow for 2 minutes, you're not going to achieve that at this low flux. Most backwashes don't last for 2 minutes. though some can do. So really the question needs to be understood both in terms of the backwash flux and the time in which it's applied. Normally in chemical engineering, it's good practice if you're trying to displace a volume from a container and you want to displace it more or less completely, it's very typical to use 3 times the volume or at least twice the volume of the free space. So ideally, we'd want to be running at something like twice the volume of the free space. So if the free space is 60 litres, ideally we'd want 120 litres of flow in order to clean out that volume. So for 120 litres of flow, you might need to be at twice this suggested flux, so maybe 60 or 70 LMH, and maybe for 2 minutes, though in worse circumstances, you could maybe reduce that to 1 minute. So this has been quite a lengthy answer to what seemed to be a simple question, but I think my feeling is that this proposed backwash flux of 30 to 35 LMH is too low. You should be operating with at least 60 to 70 if you have a backwash time of 1 minute and possibly longer, 1 to 2 minutes. If you are intending to use a shorter backwash time of less than a minute, you would have to go to an even higher flux, as some out-to-in suppliers indeed do, and you'd have to run at, say, 100 to 110 LMH with the backwash flux. So I hope that answers the question. Quite a lengthy answer, but basically telling us that we need more flux than this proposed 30 to 35 LMH. I'd now like to move on to the second question. So the second question is, what is the risk of overpressurizing the maximum pressure inlet in the UF membrane module due to water hammer? Is there any safety margin in the values provided by the supplier? So this is a very pertinent question. So just reminding you about water hammer. Water hammer occurs where you either do not have a soft start on the feed pump, so the pump ramps up too quickly, and if there is some constraint, such as a closed valve or a fouled membrane, so that the increasing flow that you create from your pump is meeting some constraint or impediment in the design. So it might meet a fouled membrane, it might be operating against a closed valve. In fact, when I look at in my troubleshooting assignments at problems of water hammer, quite often what you find is that there is a soft start on the pump, although it might be a little bit, might be ramping up a little bit too rapidly, but it's more common that the valve sequence is mistimed. So a valve opens to allow the flow, but downstream there may be another valve which is still closed and is only opening too slowly, so you temporarily get an overpressurization and a water hammer situation. There is a risk in water hammer. Most modules with an inside feed configuration have a pressure rating of around 5 or 6 bar. Those with an outside feed configuration have a pressure limit of typically 3 or 4 bar. When we looked at this in the webinars, one of the reasons is the penetration of the polyurethane or the epoxy in the tube sheet into the membrane. It's more difficult in the outside feed, therefore you tend to end up with a lower pressure rating of the module, but it's not that much lower. So typically for an outside feed module, you'd have a pressure rating of say 3 to 4 bar. So let's have a look then at, well, what are the pumps capable of delivering? Normally we use a centrifugal pump, which would have a deadhead pressure of typically 3 bar. Might be a little bit more or a little bit less. So around 3 bar. So generally, as a rule of thumb, we can expect to achieve water hammer maximum level of perhaps twice the deadhead pressure of the pump. So that's a little rule of thumb that we quite often find applies. Of course, if you didn't have a centrifugal type of pump, but you had a positive displacement pump, the overpressurization could go very much higher. But nearly always in water treatment, we're using centrifugal pumps. It's worth checking whether the system that you're talking about does indeed use centrifugal pumps. I would very much expect it to do so. So with a centrifugal pump with a 3 bar rating, it's possible, if you have one of these mistimed valve sequences, it's possible to overshoot by up to a factor of 2, so up to 6 bar. So what that means is that for an outside feed module, that would be dangerously high. It would be above the pressure rating of the module. For an inside feed module, it would be slightly above or at the maximum limit of the inside feed module. So if you have an outside feed module, the question then comes back to the second part of the question posed: is there any safety margin in the values provided? Well, the idea of the pressure rating of the module supplier is to give an idea of the pressures that could be tolerated within a whole lifetime of the membrane. So you wouldn't definitely expect it to actually split or burst or explode by simply going to 6 bar in a very temporary water hammer spike for a 3 or 4 bar rated module. But of course, you would be putting it under duress, which is outside the manufacturer's, supplier's margins. Of course, if the manufacturer knows that you as an operator did this, it would invalidate the warranty. So that's the first thing to consider. Is there a real safety issue with going over the pressure limit? I would say unlikely, but of course it's by no means ideal, but it's unlikely that you've got a real safety problem there, because in the testing to ensure, say, a 3 or 4 bar rating, you're testing to a higher pressure than that at applied level. So there is a safety margin, but of course you don't want to be going above the supplier's recommended values. So I suppose what this tells us is that we need to avoid water hammer because it's very damaging anyway to the membranes, let alone the module, and it's damaging to other pieces of equipment within the whole system. So it's highly desirable to avoid it completely and make sure that the design eliminates any possibility of water hammer. So I think that answers the question that you're not going to break the system by water hammer in all likelihood, but you would be outside of warranty, and it is a poor operational practice to allow it to happen. I do, in troubleshooting, quite often come across problems of water hammer, and normally it's a sign of a few different issues being incorrect with the system design, and it's a sign of membrane fouling, and it's clearly very important that all those issues are addressed to ensure long-term stable operation. Maybe we could move to the next question. So for the backwash system, is it not more logical to remove the waste from the bottom part of the modules than from the upper nozzle or connection? Why is the reject taken out from the top? So this is another question that I've given a little bit of thought to, and of course it does seem illogical, as the questioner suggests, to remove from the top rather than the bottom, because our assumption is that the particles that form the contaminants in our water supply have a higher specific gravity than water and should naturally drop in the module. So that's our clear assumption. So let's examine that assumption. So when you think about the backwash process, you have one force which is acting to take the particles downwards. That's the fact that the specific gravity is normally greater than water, and therefore you'll get a level of settlement naturally occurring with particles moving down. But then you've got two forces which are applying on those particles which tend to take them up. So the first of these forces is that if you use an upper offtake of the backwash water, there is a velocity of water rising up through the module. It creates a drag on the particles and will tend to try to take those particles with it. Those drag forces will tend to take the particles to the top of the module with the water. The second force that will tend to take the particles up is that if you apply an air scour for the length of time that the air scour is actually applied, which is not necessarily for the whole backwash, but for the length of time it's supplied, there will be air bubbles rising. Those air bubbles will tend to possibly attach to particles, and the buoyancy of the air bubble will tend to take the particle upwards, and it will tend to, as it rises chaotically through the liquid, it will tend to push the particles up the module. So there's two forces applying an upward force to the particles, and there's one force, the specific gravity, which is applying a downward trajectory. So of course you might say, well, if I was to take the backwash effluent or waste from the bottom of the module, my velocity, the second of the forces that I talked about, the drag would be applying a downward pressure to the module, and then the only force applying an upward pressure would be that of the rising air bubbles and air scour. So I suppose the next thing I should say is, well, let's look at this specific gravity force. So is that a big force or is it a small force relative to the other two forces? Let's think about the sort of contaminants we might have in the water. We might have sand particles or other minerals like that, which are not hydrated. They tend to have a specific gravity of between 2 and 3. So they might be sandy particles, for example. If there's a specific gravity of between 2 and 3, that means that the forces causing the sandy particle to drop through the liquid, that's a significant force because of the difference between the specific gravity of the sand and the water. So 2 to 3 for the sand, 1 for the water. So that's a big force trying to take it down. However, most particles in water supply are either minerals which are hydrated and have a specific gravity of typically 1.2 to 1.5, or they are organic in nature, and then they might have a specific gravity between 1 and 1.2, or in fact there might be microorganisms, in which case they will probably have a specific gravity of less than 1, so maybe 0.8 or 0.9. In fact, when you look at the range of contaminants, it's only those sandy particles that want to drop to the bottom of the module come what may. All of the other particles I've mentioned, the hydrated minerals, the organics, and definitely the microorganisms, either are relatively neutral, or in the case of the microorganisms, actually want to float. They want to rise in the module. So what it means is that if you apply an uptake at the top, you will easily remove those particles with the additional slipstream effect of the velocity of water rising up and the additional force of the aeration and air scour. So what it means is that our selection of whether to take a backwash from the bottom or the top is not an easy it's not an easy decision to make, because you've obviously got to think about how are you going to get air out of the module. The obvious reason that a top backwash is favorable is that if there's any entrained air to be taken out, it will be much more easily taken out from the top than the bottom. So the bottom offtake is good for high density particles and no aeration, but the top offtake is good for low density particles and aeration. I think the ideal connection philosophy would be to have both a bottom and a top connection, to use the top connection most of the time and definitely during air scour, but to have the ability to use a bottom connection if you have high density particles and so on. I think I mentioned in the webinar presentation that for suppliers that don't have a bottom connection, you can have a weight gain issue, and I cover this in some detail in the troubleshooting webinar. You can have a weight gain issue where the module over time gets an accumulation of those high density sandy type of particles at the bottom that are never removed, and gradually they build up in the bottom of the module, and the module gains weight over the course of its life, much like we humans do. And so you get this progressive problem that doesn't really stop operation, but limits the life of the module. Okay, so I've given quite a lengthy answer to that, and I suppose my summary is it's best overall if you can do both. So let's move on to the next question. I was wondering if you have a list with the main suppliers of UF membranes and the type of membranes they produce, or a list of suppliers around the world. Well, of course, this is the topic of one of the webinars, and I would say that just in summary, you have two groupings which offer a number of products, those groupings being Suez and DuPont. So Suez with the Zeeweed brand and with the former IMT company after that acquisition, which is the 700B product, polyether sulfone, 7-bore lumen product. And with the Zeeweed brand, you have both pressure-driven and submerged modules. In the case of DuPont, you have the original Dow UF, you have the Memcore UF. So both of those are based on outside feed modules. The Memcore brand has both submerged and pressure-driven options. The Dow is only pressure-driven. And then in the DuPont portfolio, you now have the Inga multi-bore polyether sulfone. So it's quite an analogous range of products to the Suez range. Outside of those, you have some important Chinese suppliers such as Memstar and Beijing Origin, but those companies tend to only supply their own brand within China. Memstar has a relationship with Hydronautics for sales outside of Asia, and Hydronautics produce their own version of the Memstar product, so different dimensions and so on than the original Memstar product. And so along with Toray, you have those other two RO suppliers also supplying either UF or MF as significant suppliers. And of course, more established than either of those two companies are two of the long-serving uh, microfiltration and ultrafiltration suppliers, namely Asahi, who work closely with the Paul Corporation outside of Asia, and Pentair, who have the X-Flow product brand. So they are the sort of groupings that I think of. There are some other companies with long-established products as well, such as Koch Industries. But on the whole, the ones I've mentioned are the main companies that operate in the membrane filtration space. So moving on to the next question. What is the best type of membrane or supplier for seawater pretreatment for RO applications? And again, this is not a straightforward question. So in the Middle East, we find that there's a major application of polyethersulfone, and you find that polyethersulfone suppliers, so X-Flow and the Inga brand, are quite dominant in that region. I think one of the reasons why inside feed polyethersulfone is used is because with fairly warm temperatures, you certainly don't have any lumen side pressure drop issues in that region. If you were in a colder area, you might find ultimately that there could be some limitations. Of course, the sea never gets or doesn't normally get that cold. But for example, in Australia, we find that for the same application, Memcor is by far the dominant supplier. Obviously, partly because it's an Australian company and the customers are Australian, so there's somewhat of a bias there, or an additional driver, perhaps I should say, for selecting Memcor, because obviously it's easier and cheaper to have an in-country supplier. But for those Australian applications, the feed water, it's not cold exactly, but it's a little chilly. It's quite often down at 16 degrees. So from a technical viewpoint, there would be at least some degree of pressure drop limitation in an inside feed product brand, because you would have the pressure drop along the lumen. Normally, we wouldn't think that that becomes a limitation until you get down well below 10 degrees, actually. But it is a somewhat of a driver, in addition to being an Australian supplier for an Australian end user. There's an additional driver from the fact that the waters are colder. In the Middle East, where the waters are uniformly always very warm, the polyethersulfone inside feed has been favoured. Yeah, I suppose the other thing I should mention is that if you take away the pressure drop limitation concern, how does PVDF stand up in seawater compared with polyethersulfone? There have been some papers that have been produced on this which suggest somewhat lower fouling on polyethersulfone in some cases, and it seems to me that that has been found that you tend to be able to get a more stable flux at a higher permeability on polyethersulfone. So I think there is some technical driver towards that, but it's not, I wouldn't say that either one of the two materials is a clear winner. I would say that polyethersulfone has some limited benefits from a fouling perspective. And so then it comes down to this issue of temperature and whether there might be any lumen side pressure drop limitations. So that definitely doesn't happen in the Middle East, which is why everything is polyethersulfone, but it can happen in the Pacific Ocean applications such as Australia, and may be applicable also in California, for example. So that addresses that question, and then maybe I could move on to this question here, which is addressing the application range. So for which applications are the outside feed PDO membranes more suited, and which are more suited to PDI membranes? So another sort of question which requires a little bit of a nuanced answer. So MBR PVDF has become very much the go-to material because of chlorine resistance, and PVDF is exclusively available in outside formats. So clearly a PDO or submerged approach is better for MBR. For reuse or wastewater, PDO has also been very successfully applied. You've potentially got a solids issue with anything to do with wastewater. So there's the possibility that lumens of inside feed formats could become plugged. In reality, I very, very rarely come across lumen plugging on wastewater reuse applications. And actually, polyethylsulfone has been successfully applied to these projects in the Middle East, where with the higher temperatures, you don't have any lumen side pressure drop issues. And in fact, the solids are not that great to overwhelm an inside feed format. So I think you can use PDI on the reuse. On the whole, people have been quite conservative in selecting PDO, so you find that that is a market leader in this application segment. For pretreatment of RO, I think it favors polyethylsulfone where you've got fouling concerns, and there is more application in seawater, as I explained, for polyethylsulfone. So polyethylsulfone and PDI will definitely be used, especially where you don't have any lumen pressure drop concerns. There has been a tendency from some of the PDI suppliers to slightly widen their lumens from 0.8 as originally used to 0.85 or 0.9, and this has reduced lumen side pressure drop concerns. For drinking water applications with good quality water, polyethylsulfone has been preferred where there is a virus target, although some of the PVDF suppliers have a good virus removal themselves, and so it's quite a close battle there. There's somewhat of a preference, it has to be said, for polyethylsulfone in continental Europe because there was a stronger historic development of polyethylsulfone, and in North America it's very much the reverse. There's quite a strong preference towards PVDF. I think one of the reasons for this is that PVDF has better chlorine tolerance, and there has been a tendency in North America to have more chlorine exposure, and in continental Europe to have less chlorine exposure. So continental Europe has preferred the polyethylsulfone and PDI, and North America has preferred the PVDF and PDO. So I think that covers that question, and I think we have another question about the use of submerged membranes in RO pretreatment. So there is experience of using submerged membranes in RO pretreatment and in seawater RO. So for example, Suez with the uh, they have a big reference with submerged membranes in China, and I think also in the Middle East. And I think Memcor with their submerged membranes have a big reference in Australia at Adelaide, and I think they have another submerged reference as well. I think in Australia, they tended to move away from submerged to pressure-driven outside feed for more recent applications, because the construction time of a pressure-driven system tends to be shorter on site. So you can do more off-site construction and delivery of skid-mounted equipment and shorten the on-site construction time. In Australia, where you have very high site costs, especially with remote sites, but you have high labor costs anyway. So it makes the installations cheaper going for pressure-driven than submerged. In other geographies, though, where the site costs are lower, you would have a different split between the preference between on-site and off-site work, and submerged membranes have become more beneficial in those applications. So, and then I think the final question is also to do with submerged. And then it says, in the presentation, it stated most cost effective for submerged is most cost effective for medium to high TSS or turbidity, and for lower turbidity, you may use pressure driven. So the questioner is asking, what are the values in terms of medium TSS or turbidity? What is the rule of thumb? Would it be, say, 10 NTU? And I think that's quite a good assumption to make, that 10 NTU would be the break point. So in terms of TSS, 10 NTU is normally equivalent to something like 15 to 20 ppm of TSS. And so you could pretty much say that if you were below 10 NTU, you're in the low TSS turbidity regime in terms of the feed. If you're above 10 NTU, you're definitely into the medium and moving in towards the high. So I think the questioner's suggestion of 10 NTU as a breakpoint, I think would be quite sound, and submerged would certainly start to come into its own at feed turbidities above 10 NTU. Having said all this, though, pressure-driven inside feed and pressure-driven outside feed clearly are completely suitable at turbidities of 10 NTU and above, but it's a question of compromises, if you like, that as you go higher and higher above 10 NTU, you would have to shorten run times and reduce fluxes to avoid the module housing in the pressure-driven outside case, or the lumens of the fibers in the pressure-driven inside case, to avoid those spaces becoming overwhelmed with the solids. So the pressure-driven can tolerate, and in certain cases with small flow rate scale, etc., it would be cost effective to use the pressure-driven on those high turbidity feeds, but it's a question of the combination of circumstances. So in the presentation, I talked about feed turbidity, but of course you've got to think about flow rate as well, and the combination of medium feed turbidity with high flow rate is likely to push you towards submerged. If you're at low flow rate, you probably need to get to high TSS before the submerged starts to come into its own. But then eventually, at very high flow rate, the submerged is can be the most cost-effective solution at all feed turbidity levels. So I hope that puts that into context. I was just trying to provide some overall indication of guidelines without being too prescriptive. So that concludes my answer to that question.
Yeah, that's all the questions we have, Graham. Before we end the program, we'd like to, give final remarks based on the questions to the audience.
Well, I think the questions from this session have been very perceptive and have actually nailed some very important issues within membrane filtration. So I'm pleased to be able to address them. And it's important that we consider our designs holistically. So you've got to consider the whole requirement in terms of the flow rate, the feed quality, and the type of application. And these questions have allowed me to illustrate some of those points. So I thank you very much for posing them, and I hope you find that my answers are useful.
Thank you, Graham. Thank you very much for addressing all the issues. And, as you know, this is a public program where you answer the participant questions, but Dr. Graham is also available to answer private sessions. If you have an interest on the subject, Q&A on the top subject about the UFMF membrane filtration, we can arrange a private session with Dr. Graham, and you can discuss with us, contact me for the discount. I think already know who am I, and this is my contact information. Once again, thank you all for joining this session on the know-how webinars Q&A with the expert with Dr. Graham Pierce. Thank you, Dr. Graham, once more again. Talk to you again soon. Bye.
Thanks very much.